is going to be on section 7.1, the central limit theorem for sample means. So by the end of this chapter, you should be able to recognize central limit theorem problems, classify continuous word problems by their distributions, apply and interpret the central limit theorem for means, apply and interpret the central limit theorem for sums. So the central limit theorem, or the CLT, is one of the most powerful and useful ideas in all of statistics. We're going to look at two forms of the theorem, one that involves sample means and one that involves sample sums. Both of them use finite samples of size n drawn from a population with a known mean mu and a known standard deviation sigma. The first form says that if we collect samples of size n with a large enough n, calculate each of those samples' mean, then those means will be approximately normally distributed. The second form says that if we again collect samples of size n that are large enough and we calculate the sum of each sample, then the sums will again tend to be normally distributed. The original data does not need to be normally distributed, but if the original population is far from normal, then more observations are needed for the sample means or sums to be normal. Sampling is done with replacement. So there's two videos that I have linked here that you'll also find on Canvas. One is sort of a cute one about bunnies and dragons and the normal world. And then there's one from the StatQuest that we've seen him before. Both are good, and I would recommend that you watch those, but use the links in Canvas. So suppose X is a random variable with a distribution that may be known or unknown, and it can be any distribution. We're going to use a subscript that matches the random variable. So now mu sub X is the mean of our original random variable X, and sigma sub X is the standard deviation of that original variable X. So if we draw random samples of size n, then as n increases, the random variable x bar, which is a sample mean, so those samples are sample means, that tends to be normally distributed. And now we have that x bar is a continuous random variable with a normal distribution with a mean the same as mu sub x and a standard deviation of our original standard deviation, sigma sub x, divided by the square root of n. So what we're saying is that if we draw random samples of size n, the distribution of that random variable x bar, which consists of sample means, is called the sampling distribution of the mean. The sampling distribution of the mean approaches a normal distribution as n, the sample size, increases. The normal distribution has the same mean as our original distribution, so mu sub x is the mean of our original random variable x as well as our sample means, and a variance that equals the original variance divided by the sample size, so it looks like this. And then our standard deviation of the sampling distribution is the original standard deviation divided by the square root of n. So the variable n is the number of values that are averaged together, not the number of times the experiment is done. So the standard deviation sigma sub x bar, which is equal to our original standard deviation sigma sub x divided by the square root of n of our sampling distribution, is also called the standard error. So you'll hear it called both. Our z-score, this slide says that it has a different z-score associated with it from that of the random variable x, so x bar does, and the mean x bar is the value of x bar in one sample. So it is a different z-score, but it's calculated the same way we've always been calculating our z-scores. So we take one sample mean, x bar, we subtract from that the mean of our sampling distribution, which is mu sub x, and divide by our new standard deviation, which is sigma sub x divided by the square root of n. So we're going to do some examples because it's going to make a lot more sense once we do that. But this one, the length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. Suppose a sample of size 25 is drawn randomly from the population. So if you have the Excel sheet open that we have in Canvas, you'll see here that our example 1 is our over 40 soccer players. Whenever we're doing these CLT problems, these central limit problems, the first thing we want to do is write down our new mean and standard deviation. So what is mu sub x bar and sigma sub x bar? So you can see here, this mean mu sub x bar is going to be the same as our original one, so it's equal to 2. And our new standard deviation, sigma sub x bar, is equal to the original standard deviation of 0.5 divided by the square root of our sample size. And it says over here that a sample of size 25 is drawn randomly from the population. So we're just going to put those into Excel just so that we have them in our cell references. So our mean is the same as the original one. Our standard deviation is our original standard deviation divided by the square root of our sample size. And that's where that 0.1 comes from on the slide. And now that we have our new mean and standard deviation, now we can start asking our probability questions. So remember that no matter what this original distribution was, normal, uniform, exponential, something else, the sample means are going to be normally distributed. So what is the probability that the mean of the sample is less than 1.7 hours? So we know that these sample means are normally distributed, so we can use our normal distribution just like we've been doing. All right, so here I have a picture of our new distribution. So here's the our new mean, which is the same as the original one. And then you'll notice that each of the steps is that standard deviation of 0.1. So the probability that the mean of the sample is less than 1.7 hours, we're going to use our normal distribution formula, and I'll pop over to Excel to look at that. I'm just wondering, I didn't put the picture on it. Oh, maybe actually I did. It's actually in here. You just can't see it. It's so small. So see how small our probability is? So it's this little shaded part in here. I thought it was just the blank distribution, but so we'll pop back over here. So these sample means are normally distributed. So we can use our normal distribution function. We're going to use 1.7. Our mean, so you can just type the number 2, or you can use the cell references if you want, and our standard deviation. And you know that for less than problems, we always use the word true. So we get that very small number. Now, our second question is, what is the probability that the mean of the sample is more than 2.2 hours? And now this picture is a little bit easier to read. And so we're looking for this small blue shaded area in here. And so remember, with our greater than problems, it's always 1 minus our normal distribution. So when we're calculating that in Excel, we're going to say equals 1 minus our normal distribution with our value 2.2. And then again, you can use the cell references, or if they're terminating decimals, you can just write the number in. But we want to know what the probability that a randomly calculated sample mean is more than 2.2 hours, and we get 0.0228 or 2.28%. And that makes sense with this little piece shaded over here. You could technically use the empirical rule here, right? Because that's more than 2 standard deviations above the mean. We'll talk about that later. All right, so same information. What is the probability that the sample mean is between 1.8 and 2.3 hours? So now we're looking between 1.8 and 2.3. We've seen how to do our between problems. We can do it all in one cell. Make sure you use the bigger number first, 2.3, and then the smaller number. You'll always want to have a positive probability, or non-negative, excuse me. And when I look at this, it's 97.59, and that makes sense for what's shaded here in blue under the curve. So if I wanted to do it in Excel, you could do it in those two separate cells if that's easier for you, or you can do it all in one. And again, you can use cell references if you have them here. And then I can just subtract off the other one with the smaller number, 1.8. And I can use cell references or type those numbers. And I should get 0.9759 like I did. So here's another example. So an unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n equals 25 are randomly drawn from the population. So again, you want to find your new mean, mu sub x bar. So it's the same as the original one, 90, and calculate your new standard deviation, sigma sub x bar. So that's the original standard deviation divided by the square root of our sample size. Please notice here I have a typo. It should say 25, not 15. So let's calculate that over here. So mu is 90, mu sub x bar, and then sigma sub x bar is going to be 15 divided by the square root of 25, which is just 5. All right, so our new standard deviation is 3. So let's make sure, hopefully that typo is just there and not in here. So here's a picture. We're going to calculate this in-between probability, and then we're going to find the value that is 2 standard deviations above the expected value 90 of the sample mean. So take a minute. I'm going to pause the video if you want and see if you can calculate this question here, the probability that the sample mean is between 85 and 92. You're looking for this shaded area here. We just did an in-between problem, so hopefully that is not too challenging for you. But maybe pause the video and try it yourself, and then come back and check the answer. All right, so we're going to do that same thing we did before here. And then if we go over to Excel and we type it in here, it's going to be norm.distribution with 92. We're going to have 90 as our mean for our sample means. 3 is our standard deviation for our sample means. And the word true minus the normal distribution with the smaller number, 85, 90, 3, true. So 0.6997, or I rounded also incorrectly here on the slide, I apologize, but just under 70% chance that the sample mean will be between 85 and 92. So finding the value that is 2 standard deviations above the expected value 90 of the sample mean. Remember when we did chapter 6, we saw how to do this, but we use the formula x equals z times sigma plus mu. So we're going to take that z-score of 2, multiply it by our new standard deviation, which is 3, or 15 divided by the square root of 25, plus mu sub x bar, which is 90. And so we get 2 times 3 plus 90, or 96. We did this in chapter 6, but just to show you, you could do 2 times our standard deviation plus our new mean, and we get 96. So if we had a sample mean of 96, that would be 2 standard deviations above the expected value of our sampling distribution. So remember, we just said that the standard error of the mean is a description of how far on average that the sample mean will be from the population mean in repeated simple random samples of size n. So in a recent study reported October 29th, 2012, that's not very recent, on the Flurry blog, the mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. Take a sample of size n equals 100. So we're going to find the probability that the sample mean age is more than 30 years, and we're going to find the 95th percentile for the sample mean age to 1 decimal place. So this is a greater than problem. So again, maybe pause the video and take a minute and see if you can calculate both, well, three things: mu sub x bar, sigma sub x bar, and then the probability that the sample mean age is more than 30 years. Pause it, figure it out, try those, and then come back and see if you got them right. Okay, so mu sub x bar is 34 because it's the same as our original mean. Sigma sub x bar is our original standard deviation divided by the square root of our sample size. So 15 divided by 10, or 1.5. And then the probability that the mean age is more than 30 years is that greater than problem. So 1 minus our normal distribution with 30, mean of 34, standard deviation of 1.5, and the word true. So if we pop over to Excel, first, we want to put in our mu sub x bar. We want to put in sigma sub x bar. So that's 15 divided by the square root of 100. And then our greater than problem is 1 minus the normal distribution with the number 30, comma, 34, comma, 1.5, true. So 99.62% chance that the sample mean age is more than 30. And then these percentile problems. So we saw this also in chapter 6. So we're going to use the norm.inv formula for this. We're looking for the critical value such that 95% of our sample means are at or below. And that would mean that 5% are at or above the value we're going to find. And so we use norm.inv with our probability, which in this case is that percentile, or 0.95. You can also use 95%. The value 34, that's our mean, and then our standard deviation, and we're going to find out that it's 36.5. So here we're going to do norm.inv. The probability, on the slide I did 0.95. Remember, you can also do 95%. And then I'm going to use the cell references here. And we're going to see that 95% of sample mean ages are at or below 36.5. Try it 7.3. In an article on the Flurry blog, a gaming marketing gap for men between the ages of 30 and 40 is identified. You are researching a startup game targeted at the 35-year-old demographic. Your idea is to develop a strategy game that can be played by men from their late 20s through their late 30s. Based on the article's data, industry research shows that the average strategy player is 28 years old with a standard deviation of 4.8 years. You take a sample of 100 randomly selected gamers. If your target market is 29 to 35-year-olds, should you continue with your development strategy? So, what do we need, or what are we asking? What is the probability that men aged 29 to 35 years old want to play a strategy game? So as always, we want to find our new mean, mu sub x bar. So that's the same as the original one. And we saw that the industry research showed that the average strategy player is 28 years old. So mu sub x bar is 28. And the standard deviation of the original distribution was 4.8. So we take 4.8 and divide by the square root of the sample size of 100. So we want to know what's the probability that men aged between these two ages would want to play a strategy game. So this is going to be a between problem, the probability that they're between the ages of 35 and 29. And once we do it, we find it's 0.0186 or 1.86%. So that is a very small probability that a gamer in this age group will want to play the strategy game. So they should not continue with this investment strategy. So if you want to see it here, our mu sub x bar is the same as the original one, so 28. Sigma sub x bar is 4.8 divided by the square root of 100. And then we do our in-between probability. We use 35 with a bigger number first, then our mean of 28, our standard deviation of 0.48 and the word true, and then subtract off the normal distribution for the smaller number, 29, with our mean of 28, our standard deviation of 0.48, and the word. I hit enter instead of true. Something is not sure why it's there. Not. All right, there we go. So 0.0186 or 1.86%. Cans of a cola beverage claim to contain 16 ounces. The amounts in a sample are measured and the statistics are N equals 34, so that's our sample size. X bar is 16.01 ounces. So if the cans are filled so that the mean mu is 16 ounces, which is what it's labeled as, and our standard deviation is 0.143 ounces, what's the probability that a sample of 34 cans will have an average amount greater than 16.01 ounces? Do those results suggest that the cans are filled with an amount greater than 16 ounces, which is what it's labeled as? So what is the probability that the can will be filled with an amount greater than 16.01 ounces? So again, this is what I was going to say. Find our mu, so it's the same as the original one, 16. That's what it's supposed to be. And then we calculate our new standard deviation, which is the old standard deviation divided by the square root of our sample size. So in Excel, 16 is our mu sub x bar. Sigma sub x bar is sigma sub x divided by the square root of our sample size. And the probability that the cans are filled with more than 16.01 ounces, I'm going to use the cell reference for the standard deviation here, is 0.3417. Or there's a 34.17% chance then the cans are filled with more than 16.01 ounces. So that's not a huge percentage, but if you were a manufacturer, more than a third of the cans are filled with more than the number of ounces that you want it to be. So you're sort of giving away free soda. So if you're a consumer, you might be happy to know this. But if you're the manufacturer, you might want to figure out what's going on and get that closer to the labeled 16 ounces. So that's the end of the video for 7.1.